We're taking this next step now. In the respiratory system, we're looking at blood gases. And you've seen this diagram before when we studied blood flow. So from the heart, we're going to send blood to the lungs to pick up oxygen and release CO2. We're going to come back to the heart on the left side. We're going to go out the aorta, and then we're going to supply the body with the main blood flow to the body. This is a high pressure system. We're going to address nourishment of the cells. We're going to pick up the CO2 from metabolism of the cells and come back. And I want you to keep track of what's the oxygen and what is the concentration of CO2. So here we begin, and this is something that is good to know. We just look at the air. Remember, 760 was all the pressure in the air. The air is mostly nitrogen, right? It's 1/5 oxygen. Those are the two main components. There is actually very little CO2 in the air, right? It's less than 1%. If it ever gets to be 1% of the air, you would notice it and you would say, oh, it's very stuffy in here, right? That's when it gets to approach 1%, which is a very small amount ultimately. So here's the air we're breathing. Okay, so let's begin, and we're going to be taking a next look over here at the upper right. And before I even do that, when I want to get air, or that is to say the useful part of the air for us, which is the oxygen, and I want to get it on the hemoglobin, how long does it take? It takes 1/4 of a second to fully oxygenate hemoglobin. So if you feel like you're in a stuffy room, you walk out the door or throw open the window. In 1/4 of a second, you have just added oxygen to your hemoglobin. You're fully oxygenating your blood in the fresh air. Okay, so that's 4 molecules of oxygen going on to 1 hemoglobin molecule. That's the key right there. So then let's take a look. Here we are. This is the air inside the lungs and the alveoli. What does that look like, that air? We're now at 104 millimeters of mercury, so we've lost some oxygen, and we have actually plenty of CO2 inside the lungs. This is the standard amount, 40 millimeters. That was compared to 1/3 of 1 millimeter. We've gone to 40. So that's just what we're working with. Okay, then we come in here and we're going to be looking at the blood next. What does the blood take from that? The blood is going to be basically equilibrated across the 40 here. So there's 40 millimeters in the air of the lungs. There's 40 millimeters in the blood. There's always a certain amount of carbon dioxide in here, and it's going to be mostly, how shall I say, carried as bicarb. So we always have something here which is a buffer. You could say there's a certain level of buffering. We'll get to that eventually. Okay, so basically right now we're thinking to ourselves, I'm at 40 millimeters of mercury of the CO2. I have this nice little round number here, and I want you to always remember this, that when we breathe oxygen from the air into our blood, we're at 100 millimeters of mercury. Very handy. We've got a round number to work with. So that then takes us down over here to the cells. What's going on at the tissue level? What does that look like? And so now we're looking at 40 millimeters of mercury of oxygen, 45 of CO2. Okay, that means that there's been an uptake, a tremendous. It's gone from 100 down to 40. These are in the tissues. Okay, and the tissues themselves have a little extra CO2 because the cells are metabolizing. Okay, so we're getting the oxygen in, we're picking up the excess CO2. This is inside the tissue, right? So we've left the bloodstream. Then we're over here now. blood leaving and coming back up, we're still at 40. So on the venous side, when you look at your veins on your arms or legs, you're looking at blood which is only 40 millimeters mercury of oxygen. So we have less than half. Remember, we were at 100, now we're down to 40. We were at 40 and now we're up to 45. Actually, that's not a huge change, is it? The really big change was in the oxygen. The very minor change of 40 to 45 was in the CO2, and that's what's in our venous system. And now we're back at the heart, and we're going to come up this side again, and we're going to be delivering right out here, out to the air. That's what's out on the air, and we're now back in the alveolus, and we're back, that's what it looks like in the alveolus of the lung. This is what it looks like just on the other side of the diffusion barrier in the blood. We're back to 140. So I need you to have that little cycle in mind. Over at this page over here, this is page 827 in my book, and I want you to sort of take a look at this diagram and notice that we have to have coupling. That if we have a lot of air, we need to have a lot of blood flow. So they have to match each other. That's called coupling. If we don't have very much air, then and we don't really need to have very much blood flow. So these things need to be coupled, and I need you to take a look at what is going on in this diagram and what's being expressed. Okay, then we press on to the transport and the nature of how delivery works. So take a look at this diagram. Notice that things are flatter. When we get to this flatter thing here, we're looking at temperature. 38 is 98.6. 38 Celsius, 98.6 Fahrenheit. This is normal body temperature. If it gets warmer, guess what? The oxygen offloads more readily. Okay, that means that wherever the blood goes and it meets up with a tissue that's a little bit warmer because that tissue is working, maybe you're walking or running, and so those muscles are working and the temperature of the muscles is higher. That means preferentially those muscle cells are going to get more oxygen because the oxygen comes off the hemoglobin more readily. Okay? Over here in this one, we're looking at pH. Notice that the pH here, this is the normal pH, is 7.4. Here's a pH that is a little bit more alkaline at 7.6. Here's a pH that's more acidic at 7.2. What do we know about metabolism is that it produces a lot of CO2, which is acidic. So this red line here represents the metabolizing and more acidic aspect of the blood that's near the working organs and tissues like muscles. And again, we're going to have the easier offloading of oxygen. So that's what's going on in this diagram, is it's telling us that oxygen will be delivered preferentially and more easily to any tissue that is producing more CO2 or working harder and having a more acidic pH. That tissue will also be warmer because it's working. Okay? And so again, the oxygen will be preferentially delivered there. Okay? That ends this particular episode.